Now we'll see some applications of magnetic field induction on axial line and equatorial line. Suppose if you take two bar magnets of identical magnetic moment M and M are arranged at the corners of a square of side A. What is the magnetic field induction at this corner? At D, you can think they place magnets at A and C, and at D we want magnetic field induction. For this bar magnet, there is a point on axial line. That's why what is magnetic field induction due to this bar magnet here? For short bar magnet means mu naught by 4 pi 2m by a cube. And what is the direction here? You see, on axial line, magnetic field induction is same direction as magnetic moment, south to north. So here also like this. So magnitude and direction along x-axis, that's why you can take a I direction. Now due to second bar magnet, this one, there is a point on equatorial line. On equatorial line, what is the magnetic field induction for a bar magnet? Mu naught by 4 pi m by a cube. What is the direction of magnetic field induction on equatorial line? Means it is opposite to magnetic movement. Magnetic movement from south to north like this, south to north like this, and that should be opposite direction. So these two are opposite, then you can subtract B1 minus B2. B1 is greater, that's why. Then what you get, net field at that point is mu naught by 4 pi 2m by a cube due to first bar magnet, and due to second bar magnet, this one is along positive axis, other is along negative axis, and finally you get mu naught by 4 pi m by a cube I cap we get. Same situation if bar magnets are arranged like this. And in the previous case, you see, this magnet position is not changing, only this magnet position changes. Position means alignment changes. See here, and in this case, the position of the magnet is parallel to this bottom or baseline, and here perpendicular to baseline. Nothing but it is along this vertical line. Now what is the field here? Now this is a point on axial line of this bar magnet. For this bar magnet also axial line. Then what happened? This field is not changing. Mu naught by 4 pi 2m by a cube in I cap, and this you get vertically up here. Why? Because on axial line, field is acting in the direction of the axis, magnetic axis, south to north. So here also acting up. But what is the amount of field? Mu naught by 4 pi 2m by a cube here, because that also axial line only. So two fields are perpendicular to each other. We can calculate net field. What is two fields? B1, B2 are perpendicular. Then what do you get net field? B net is equal to square root of B1 square plus B2 square whole root. So that you can substitute 2 mu naught by 4 pi m by a cube whole square plus same 2 mu naught by 4 pi m by a cube whole square. If you do square root, and you get 2 root 2 mu naught by 4 pi m by a cube. Otherwise, if you want vector notation, you know that this much amount mu naught by 4 pi 2 m by a cube along positive x-axis, the same amount along j-axis. So take this value common, then what you get? I plus j you get. This is a vector notation of magnetic field induction at this particular point. Now we'll see comparison between a bar magnet and a current carrying coil. Suppose you can assume a coil is carrying current I, so it is rotating. And in moving charges and magnetism, we have one concept: a current carrying conductor can create magnetic field. So how much strength of the field it can create? What is a magnetic field induction it can create? Means that is magnetic field due to a coil is this you get B coil is equal to mu naught n, number of turns in the coil, I, how much current is carrying, and 2 into radius of the coil. What is the radius of the spiral here? That you get one equation. And for bar magnet, what is the magnetic field induction on its axial line? That is B magnet is equal to mu naught by 4 pi 2m by r cube here. So this is equation 1, this is equation 2. If you are comparing these two, if you make it equal these two, then what you get? For bar magnet, mu naught by 4 pi 2m by r cube is equal to mu naught ni by 2r. So after cancellation, m magnetic moment is equal to pi r square ni we get. What is pi r square? Area of the coil, this face area of the coil. N number of turns in the coil. I current carrying. So magnetic moment of a current carrying coil we can write as so pi r square area and number of turns into I. So magnetic moment M is equal to NIA we can write. A is pi r square, that is area of the coil here. Now let's see magnetic flux. First of all, we know what is magnetic field induction. Magnetic field induction they define as the force experienced by unit north pole at a particular point. We can call it as magnetic field induction at that particular point. Like that we can define. Another definition also there. We know where more magnetic field is there, where less magnetic field means if lines of magnetic lines of force are crowded, we can say more magnetic field. And less crowd, rarer is there means less magnetic field we can say. That means magnetic field induction depend upon crowdedness or number of lines of magnetic flux. So magnetic field induction can also define as, then can also called as magnetic flux density. What is flux density? Flux by area. What is flux? Magnetic flux means how many magnetic lines of force are passing. So pi represent magnetic flux and A area. So what is magnetic flux density or magnetic field induction? That is flux per unit area. If you modify this formula, pi is equal to flux pi is equal to BA we can write. But this we can't apply for all the cases. Why? Because you can see here one example. The flux lines are like this. Think like uniform field. Magnetic field induction is B. And area of the coil, area of a plate or area of a surface you can assume like this. That area is A bar like this. Direction of area perpendicular to surface of that body. So that's why should take a normal on the circular part, normal on the circular surface like this. Now how much flux is passing through this means suppose if this surface is like this vertical, we can say maximum flux is passing. Suppose if it is like this, no flux is passing. That means flux passing through area is depend upon magnetic field induction there, and area of the plate also, area of the plane also, and other factor also depend. That is what is the alignment between B bar and A bar. If B bar and A bar is 0, you get maximum flux. If these two are perpendicular, then you get minimum flux. So flux pi is equal to BA cos theta if angle between A bar and B bar. And A bar means normal to surface. Normal to surface and magnetic field is 0, then you get maximum flux. So AB cos theta means what you get? A bar dot B bar. Now similarly here we get B bar dot A bar we get. So magnetic flux passing through a closed surface, how we can calculate? That is B bar dot A bar. If you know alignment also, you can use BA cos theta. Here important point, magnetic field induction can also called as magnetic flux density. And magnetic flux units are Webers. Units are Webers. So we can write B is Tesla or Tesla meter square. Area is meter square, Tesla meter square we can write.